Hey y'all, today we're going to talk about how interparticle forces will impact melting and boiling points of different substances. Now we've already kind of touched on this in a couple of other videos, but we're going to be really explicit about it in this one. All right, we're going to talk about the actual processes of melting and boiling as well. So let's get started by remembering that solids, liquids, and gases of the same compounds are differing from each other simply in the arrangement of the molecules themselves. So a solid, the molecules are going to be arranged in a fairly stable and well-organized structure. Liquids, those molecules have moved apart only very slightly, but more specifically, they're simply moving around and past each other. And then in gases, those molecules have been blown apart as far as possible to the point where you've overcome all interactions and the molecules are essentially independent of each other. Keep in mind, when we melt things, all right, that are covalent molecular compounds, such as water, going from ice to water to gas, the molecule of water did not change. Melting and boiling do not change the actual chemicals themselves in molecular compounds, okay? What it does is it simply changes their arrangement, their organizations, and it takes energy to do that. We talked about this in thermochemistry, where when we heated the compounds, when we heated the substances, energy went in either in the form of kinetic energy or potential energy. Changing phase is a change in the potential energy of the compounds. So today what we're going to look at are going to be how those changes in potential energy, melting and boiling, play a role with the actual interparticle forces themselves. Now, the first property we're going to need to look at is simply the melting point. At which temperature will the substance go from a solid to a liquid? Now, this will differ based on the interparticle forces. The stronger the substance is held in its solid form due to stronger interparticle forces, the higher that melting point is going to be. So substances with high melting points also have very strong interparticle forces. Substances with lower melting points have much weaker interparticle forces. Now, this is often a piece of direct evidence for ranking interparticle forces. But in general, ionic compounds will have very high melting points because their interparticle forces are strong due to Coulomb's law. Meanwhile, molecular compounds tend to have weaker interparticle forces, all right, because they're more constrained by dipole-dipole forces or by London dispersion forces and therefore have lower relative melting points. Now, one thing to be aware of is that boiling point is actually a better representation of interparticle forces than melting point is. It correlates very closely, but in general, melting points might not be as affected because the molecules or particles themselves aren't completely separating. We often use boiling point instead because what you have essentially done when you boiled something is you've taken those particles and blown them apart as far as they go, essentially separating them such that there's no or relatively no interaction between the particles at all anymore. So when we're choosing between melting point and boiling point, I tend to choose boiling point to look at as opposed to melting point because it does a better job of representing true interparticle forces. But the correlation is the same. The higher the boiling point, the greater the interparticle forces. The lower the boiling point, the weaker those interparticle forces. The other thing that this relates to are some of the properties of these compounds. So even if we're not melting and boiling directly, we could be discussing vapor pressures. Now, if you remember back to our conversation about vapor pressure in our gas law unit, vapor pressure is the amount of the liquid that vaporizes at the temperature of the atmosphere, of the region around it. So water, by its nature, will start to evaporate even if we're below boiling point. If I spilled water on my desk, over time, that water will evaporate. Because all of this is constrained by the Boltzmann curve, some molecules do have more energy than others. We are naturally going to have a process that favors evaporation over time. Vapor pressure is going to correlate along with those boiling points and melting points. The higher the boiling point, the lower the vapor pressure. The lower the boiling point, the higher the vapor pressure. So when we look at vapor pressure, what we're thinking is these molecules are particles that have escaped the liquid form. So again, melting point, boiling point, vapor pressure, all very highly correlated with the strength of interparticle forces. One other thing that is affected by interparticle forces is going to be the ability to mold a substance. So if we think about butter, butter can be molded, right? It can be shaped. You can squeeze butter and you can cut butter very easily, relatively speaking, because the interparticle forces between the butter molecules aren't exceptionally strong. But as those interparticle forces become stronger, let's say into an ionic compound where it's extremely strong, now we start to see forces that are more in play that lead to brittleness, which is a shattering effect. Remember, crystal lattice structure of ionic compounds minimizes the repulsive forces and maximizes the attractive force. Once we start to break down that lattice structure, it doesn't just gently decompose. It doesn't just gently break. It shatters, okay? And the reason it shatters is because those ions do have extremely strong levels of attraction and or repulsion. So they tend to be very hard, but when they do break, they shatter. Now, one thing we really haven't talked about a whole lot is metal. Metals tend to exist in a kind of a weird place when we talk about interparticle forces. And the reason for that is because they don't necessarily obey all the rules you expect. Metals, remember, have around them a sea of electrons when they're in the solid form. So metals, by their nature, don't tend to have extremely strong attractive forces with each other. So they tend to have lower melting points, but that's not always true. Some metals, especially alloys, can have extremely high melting points based on the interactions between the nuclei and electrons involved in the actual metal itself. So it's hard to really state anything unequivocally for metals in terms of melting point, but it is safe to say for metals that they do conduct electricity well in their solid form because of the C electrons. Covalent compounds, ionic compounds, well, they don't conduct electricity when they're in their solid form. The other thing is ionic compounds, when you melt them or when you dissolve them in water, now they do conduct electricity because those ions are now able to move around, and as a result, electricity can be conducted across the system. So let's summarize today's video. Today we looked at how interparticle forces of different compounds, ionic, covalent, or metallic, can impact the properties of those compounds. We looked at melting point, we looked at boiling point, we looked at conductivity, we looked at brittleness or malleability. But one thing is clear here: the stronger the interparticle forces, the higher the melting point, the higher the boiling point, the greater brittleness, and the greater energy it takes to start to separate out those compounds. Please keep in mind, though, that when we melt covalent compounds, when we boil covalent compounds, we are only separating the component molecules. We are not breaking covalent bonds. When I melt water from ice, it's still water. When I boil water to a gas, it's still water, H2O. So please, please, please do not forget that we are only separating interparticle forces, intermolecular forces, not the covalent bonds themselves when it comes to melting or boiling covalent compounds. Covalent compounds do not conduct electricity because their electrons are held tightly within those covalent bonds. So electrons can't move through a covalent substance, okay? This is obviously different than the ionic in the liquid form and the metals in their solid or liquid forms. Ionic compounds in their solid form do not conduct electricity because of the fact that those ions are held tightly within the crystal lattice structure. Ions cannot move, electrons are not moving through the compound as a result, so they do not conduct electricity. Thanks for watching today's video. I hope you enjoyed it, and I'll see you in the next one.